hey, they're paying not to be here, and they pay in more ways than one. I think more people are going to come.
Maybe.
Oh. All right. All right, well, seems as good a time as any to start. Oh! Wow. My patience has paid off.
Does CJ still show up to these?
What's that?
Does CJ still show up to these?
I'm missing. Although slightly higher attendance since I started doing this. But students, I tend to, they seem to not like a flipped classroom. Would you guys like a flipped classroom? Or this would be like a flipped classroom, but you watch all the lectures online, then you come and do this. Would you like that?
I tried that once in high school, and then you ended up just doing the homework at home because you wouldn't finish it in class. And then you would also have to do the lectures and everything else at home. So it basically just turned into just a bunch of homework.
Yeah.
Not a lot getting done in class. At least that's my experience.
I've never done it. But we're going to try next semester is we're going to have so Dr. Tibbetts and I, we're going to have designated times in the classroom that we'll sit and let anyone come in. So we'll see if that works. We're talking about flipping the classroom, and Dr. Tibbetts might, and I don't think I would. But well, we might have to cancel a section in enrollment slow. Anyway, that's a different discussion. Different time for different day. All right, well. So same idea. I'm going to solve a problem, and you can solve a similar one. And these are specifically hand-selected because they're similar to questions on the test. So this is not like we're just doing this for your edification. This is direct studying for the test. Okay, so titration problem. There's two ways to do this problem. You can do the moles acid equals moles base. So what you can do is calculate out the moles of sodium hydroxide, then note that there's a 1-to-1 molar ratio of sodium hydroxide to perchloric acid. That's HCl4 is perchloric acid. And then divide by the volume to give you molarity. That's one way you can do it. Or you can do dimensional analysis, which never fails. The dimensional analysis way is this. So there's the same idea of the moles acid is moles base. So it would be 0.2 moles NaOH per liter times 0.02262 liters times moles HCl4 to mole NaOH divided by 0.025 liters. And if you do that, you get 0.181 molar. And next thing is I look, does this make sense? So I think it makes sense because, so the 0.2 molar, you need 22 milliliters of that, and it's 25 milliliters. So that means that the unknown sample is lower in concentration because you need less of the more concentrated stuff. But it's not too far apart, so yeah, it's about right. So that looks like it's pretty good. I guess I have 4 sig figs. Oh, that's right. Okay. So now then do 90. And something to note is the 3-to-1 molar ratio of the sodium hydroxide to the phosphoric acid. Yay, we got more.
So it doesn't have to be on opposite sides. How it's like mole of NaOH, mole H3, because usually we will calculate the
Oh, I see. No, it's just the ratio. It doesn't necessarily have to be on opposite sides.
okay, and then why is the meters down at the bottom?
Because that's molar capital M. Molar means moles per liter.
Is that 0.1 NaOH?
Yes. So molar capital M is moles per liter. So we say 0.1 molar, 0.1 M, that's 0.1 moles per liter. If you look at the dimensions, so we just cancel, and now you have moles of sodium hydroxide here. And now you convert to moles of phosphoric acid here, and you divide by the volume. So now you have moles of phosphoric acid divided by the volume of the concentration.
And then this is a mole.
Well, no, not that. Just that's right. One more. We don't need the M
Or
there. M, capital M means moles per liter.
Oh, 30 milliliters. Okay, so
No, there's no mole. There's no mole. It's just blank. Because if you look at the
Oh, then this cancels out, that cancels out.
this unit
Oh, no.
units cancels. And then
Okay, so we want to
moles cancel. And then the mole, you get the units are mole, each mole acid per liter. So a molar acid.
Okay, so yeah, we want to keep the moles.
Yeah.
On
Or whatever per liter. Yeah. A mole and then we leave them up. It's not one mole. That's just the units.
Oh, just like it. Yeah, I get it, but at the end.
Yeah. Should get. What's your 2 not 1? Yep.
Okay.
Is that making sense?
Yeah.
And then this is just the ratio of this 1 to 3. It's just like a recipe. It's like, I don't know.
Yeah.
If I'm making Kool-Aid and I need 2 scoops per pint, and if I have 3 pints, how many scoops do I need to put in? Okay, everyone's favorite topic is oxidation states. I had a student earlier today, I think it affected her academic self-esteem as we were doing these problems. So you saw the given information I gave out, right? And this chart is in it. So you will be given this on the final. Do not print it out yourself. I will do that for you. But here we go. So you're given the rules of oxidation states. And let's just go ahead and assign some of these. And these rules are hierarchical, meaning rule number 1 is more important than rule number 2. So assign each atom, element, or ion an oxidation state. So silver, number A, it's a free ion, or I'm sorry, free element, so its oxidation state is 0. Silver plus 1 ion, its oxidation state is the charge of the ion. So 1, 0. And now for C, calcium fluoride, the sum of oxidation states in a neutral molecule unit is 0. So this means that calcium plus 2 times oxidation of fluorine equals 0. And then we have to go back to the chart, and alkali metals have an oxidation state of plus 2. So that means calcium is plus 2. So plus 2 plus 2F equals 0. That means fluorine is minus 1. So calcium is plus 2 and fluorine is minus 1. So how are you going to start questions with this one? Same idea, hydrogen sulfide. 2 times hydrogens plus sulfurs is 0. And then you go down the list, and then go to the chart, and then these are also hierarchical. You get hydrogen to being +1, so you have 2 times +1 plus sulfur is 0. Sulfur is -2. -2, so +1 -2. And E, carbon plus 3 oxygens equals -2. And this is rule number 3. An ion is equal to the sum of all the oxidation of all atoms in an ion equals the charge of the ion. So there, carbon plus 3 oxygens is -2. Oxygen tends to be -2, so carbon plus 3 times -2, 0 -2. So 3 times -2 is -6. Add 6 to both sides. 6 plus a -2 is 4. So carbon is 4. So carbon is +4. Oxygen is -2. And then chromium and oxygen. So chromium plus 4 times oxygen is -2. Oxygen tends to be -2. Chromium plus 4 times -2 equals -2. 4 times -2 is -8. Add 8 to both sides. -2 plus 8 is +6. Chromium is 6. So chromium is 6. Oxygen is -2. So any questions on how to do those?
A and B is the same element?
Yeah, the difference is...
Oh, it was a minus, okay. Or it was a plus.
Yeah. Yeah, this is 0 and this is +1.
Okay. Can I just copy that down?
Alright, so give it a try with... You can see, see the chart. Or how good my vision is if I can see the chart. Oh, what? I can see the chart, I just can't read it.
What if we wrote it down and just have the chart up?
I guess I could just put Yeah, I put them in really small. I used to play a game called Chemistry Mahjong that you had to like connect up oxidation states to solve puzzles. So I got really good at doing these quickly. Maybe it's the way it is, like, this out, this out. So we're doing this kind of Korean model, like solve a problem with problems to solve. So, and we're reviewing some oxidation states. So it's not equal to 0, it's equal to minus 2, so the sum of the ion charge. 2 times Cl plus 7 times oxygen is minus 2. When it rolls, oxygen is the minus 2. So 2Cl plus 7 times minus 2 is minus 2. So 7 times minus 2 is minus 14. So you have 14 on both sides. So 14 minus 2 is 12. So 2Cr is 12. Cr or Cl is 6. hydrogen can also be -1. Something called mineral hydrides. You can play around on here. Okay, so numbers are on the side, so I can look at it later. Okay, determine if each reaction is a redox reaction. Redox is reduction oxidation or an oxidation reduction. For each oxidation reduction reaction, identify the oxidizing agent and the reducing agent. So if you recall oxidation reduction, oxidation means loss of electrons, reduction means gain of electrons. So this is an electron, so I've just been oxidized. I've lost my electron. Gaining electron is reduced. So the species that's oxidized, I'm being oxidized, I'm delivering the electron, I'm the reducing agent. The element that is reduced, so by reduced, I grab this, I'm causing oxidation, I'm the oxidizing agent. So another way to think about it is, I know it's opposite, think about like James Bond. James Bond has a license to kill, he delivers death, he's the agent of death. He never dies, he delivers death. So just like an oxidizing agent delivers oxidation, but itself is not oxidized, it's reduced. If that makes sense. That's the way I always kind of thought of it. So, okay, one of the easiest ways is to get the oxidation state for everything. Oxidation state, so lithium, it's 0. Oxygen is free element 0. +1 here, -1. So we do have a transfer of electrons. And lithium is being oxidized. Oxygen is being reduced. So lithium is the reducing agent. And oxygen is the oxidizing agent. And then for B, magnesium starts at 0, iron is +2, magnesium goes to +2, iron is 0. So magnesium is losing electrons, it's oxidized, iron is gaining electrons, it's being reduced. That means magnesium is the reducing agent. And then iron +2 is the oxidizing agent. So next one here, lead +2. Nitrate and sulfate doesn't change, so I'm not going to even put them. Lead +2, sodium plus. No electron transfer, so this is not a redox. No redox there. And HBr, hydrogen's plus, bromine's minus, potassium's plus. Oxygen is -2, hydrogen is +1. Water, hydrogen is +1, oxygen is -2, potassium plus, bromine -1. This one here, there's no redox. Nothing changes oxidation state. Does anybody have any questions with this? I'm sorry, I know it's kind of small. Questions with this at all? Okay, since you've already proven you can do oxidation states, I'll just go ahead and list them on here for you. So state whether it's an oxidation reduction reaction, and then identify the oxidizing agent and the reducing agent. reducing agent is not always written first. So. Anybody stuck? Raise your hand if you're stuck. James, you stuck, or you just kind of you
Just scratch it.
Okay. Does anyone want anything explained? None of them explained. If not, I'm going to keep on going. Or you guys are still. You guys still listening? These are obviously unbalanced. Actually, oh no, it's not. Never mind. It is. Sorry, mistaken. Okay. All right, then next one. Okay, you'll be given this equation with the URMS is 3RT over M, where M is kilograms per mole. So I'm just going to do it for fluorine, but F2 is 38 grams per mole. Chlorine is 70.9 grams per mole, and bromine is it 79 something? What is bromine? Is it 79.1? 79.9. So it's going to be 159.8. So grams per mole. So in terms of speed, so the lighter ones move faster. So the lighter ones move faster, so they fuse faster. So F2 is going to be faster or greater fusion than Cl2, which is going to be greater than VR2. So, are you okay with the effusion rates? Just the lighter one's faster? Okay. So the root. What? Okay. What is that? So it says calculate the root mean square velocity and kinetic energy of. Well, we don't have to do kinetic energy.
So yeah, just because of their size.
What do you mean? Oh, the size. Yeah,
Small.
they're specifically their mass. Yeah.
Okay, makes sense.
I'm not going to do kinetic energy because that's not on the test. Kinetic energy is 1/2 mass times velocity squared. So, well, I mean, you could argue that kinetic energy is 298 Kelvin because that is their kinetic energy. But and rank, it says rank these halogens with respect to the rate of fusion. So fluorine is faster than chlorine is faster than bromine. Gets a mass. And the RMS velocity, 3RT over molecular weight. And if you remember the given sheet, this is given to you. So 3 times 8.314 times 298. There's only the Kelvin in there. Molecular weight is 0.038. And do all this to the half power. Half power square root 3 times 314 times 298. 442 meters per second. So why don't you do for carbon monoxide, carbon is 12, oxygen is 16, sulfur is 32.
And the bottom one is in kilograms?
Yeah. Last class had a question about the units, which ones to use, how it all works out. So it's right there. both have a hard time seeing. You have a hard time seeing. Does that help, or is that put on the screen?
No, it's fine.
Yeah, no worries. No, divided by the mass of carbon monoxide in kilograms. So carbon's 12, oxygen 16, so 12 plus 16 is 28. That's 28 grams per mole. So kilograms divided by 1,000, that's 0.02. Do you understand what I mean? So I'm not trying to make it go sorry.
It's okay.
I'm the other teacher reach on your shoulder. What's up?
I just read everything off.
It's the same thing here, just it's answering two things. Square root of that. Did you want the first number?
It's okay.
You said we're not doing kinetic energy?
No. You have to do 1/2 mv squared, but the other thing is temperature means average kinetic energy, so you can argue that the kinetic energy is 2 million Kelvin. What you find out is that they're the same for all three. But that's what it means. That's what temperature means is average kinetic energy. So, argue. You get 5.5. Okay. So rather than, I'm just going to explain these two. So this graph shows molecular velocities at different, so for two different molecules, the same temperature, which molecule has a higher molar mass, which one has a higher rate of effusion. So y-axis number of molecules, x-axis velocity, the speed. So the heavier gas is going to have a much more narrow distribution. So A is the heavier. The lighter one's gonna have a much more broad distribution, so B is the lighter one. So the other thing is that they have the same energy, and B is moving faster. So this peak here is the root mean squared velocity. These are the peaks of the RMS. So if they have the same amount of energy, and this one has lower speed, that means it's heavier. So it's moving more slowly, but has the same momentum. Well, not momentum, but has more momentum. And then the lighter one, to have the same amount of energy, is moving faster. So like if a car and a truck have the same energy, the car has to be moving faster than the truck because the truck is heavier. So likewise, this gas is heavier, so it's moving more slowly, and B is moving faster. The faster one to fuse is faster, so B is going to fuse faster than A. So, make sense? Okay, and same idea. Number of molecules, velocity, which one's low temperature, which one's high temperature. Low temperature, so temperature means average energy, and this is the same gas. So average energy, average kinetic energy, and the RMS is here, so the peaks. So this one is moving slower, more slowly than this one. So T1 is moving more slowly than T2, and the slower means lower temperature. So also the lower temperature has a more narrow distribution, the higher temperature has a broader distribution. So T2 is higher than T1. So however you want to look at that. So if you want to look at it in terms of kinetic energy, if you want to look at it in terms of how broad things are, so kinetic energy, higher temperature has more kinetic energy for the same gas. So actually for all gases, because temperature means average kinetic energy. So the other thing is that a cold temperature has a narrow distribution, a high temperature has a broader distribution. So, questions with that? Okay. Consider this chemical reaction here. So carbon plus water forms carbon dioxide and hydrogen. How many liters of hydrogen gas are formed from the complete reaction of 15.7 grams carbon? So assume that the hydrogen gas collected at a pressure, 1 atmosphere temperature of 355 Kelvin. So this is bringing stoichiometry into gas laws. So the idea is starting with carbon, figure out how many moles of hydrogen gas there are, then by using the ideal gas law, figure out the volume. So let me do that for you real fast. So we're given 15.7 grams of carbon, mole carbon to 12 grams carbon, and then mole H2 to mole carbon. And in doing so 15.7 divided by 12, we get 1.31 moles of hydrogen, and PV equals nRT, which implies volume is nRT over P, 1.31 times 0.08206, temperature 355, all over 1 atmosphere. That's right, atmosphere there. .1 liters. Okay. So once you try your hand at 72, water 18 grams per mole, and So this is what mass of water is required to form 1.4 liters of oxygen, a temperature of 315 Kelvin, a pressure of 0.957 atmospheres. So what you want to do is get the number of moles. So the N oxygen from those data, then get the N water, and then get the grams of water. And don't forget that there is a 2-to-1 molar ratio between the oxygen and the water. So you need twice as many moles of water as you do oxygen O2 gas. Let's try it out. Anyone getting stuck? Yeah, I'm putting 1.9 there because of the 2 sig figs. 1.4 liters. I mean, if not, I'm getting the 1.8659517. Blah, 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 blah. Okay. And the dreaded Hess's law. There is a question like this on the final, and it's easy. I consider these two problems to be easy. So, just a real simple one you can do quickly. calculate the heat of reaction for this reaction. Fe2O3 plus 3CO makes 2Fe and 3CO2 using these two equations. So when you do these, well, first of all, I call this one H1, I call this one H2. And you have to put the reactants on the left and the products on the right. So looking at this first equation, so, oh, that's a little slow. Is the internet getting slow? So Fe2O3 is on the wrong side, so we're going to have to flip this one. And then CO is on the proper side, CO2 is on the proper side, so we're going to leave this one, the bottom one, as is. So let me flip the first one. Oh, now it's working fine. Now we're going to leave this one. So, but notice we need 3 COs. So we're going to multiply the bottom one by 3, like so. And now when we add them together, the 3 O2s cancel, and we're left with Fe2O3 plus 3CO yields 2 iron plus 3 CO2, and then it's minus H1 plus 3 H2, like that. So let's see if you can sort out the next one. Hopefully you're seeing you leave the first equation as is, and you flip the second one, but you have to divide the second one by 2 to get it all to work out. And then when you add it together, you get the equation you want, and that's the first heat minus the second heat divided by 2. I'm not going to ask you to calculate it out. Just, you know. Does anybody have any questions with this one? Students usually hate this stuff. There's only one question on it. If you're having a really hard time with it, it's probably not worth the point to effort ratio to do it, especially if it's multiple choice, so you can guess it. Right, so that's how it's going to be an easy one. Like, well, I consider that easy. I mean, it might be different for your experience. It's going to be one that's not like you have to do multiple step and do a lot of that. It's just take one, divide it by or look at it, and it's very, very quick one. But okay, now we're going to combine stoichiometry with energy. So what mass of natural gas must burn to emit 267 kilojoules of heat? So, and so we need, 207 kilojoules. Oh, geez, that's ugly. Kilojoules. And then we have mole CH4 to produce 802.3 kilojoules. And then 16 grams CH4 per mole CH4. So you needs to emit, so 267 kilojoules is going out, and it's a negative reaction, right? So that means that for every 1 mole of CH4, 802.3 kilojoules of heat are produced. So ratio mole CH4 for every 802 kilojoules, and then 16 grams of that, it's going to be about 4 grams of that. So this is just dimensional analysis, but then using stoichiometry from the equation. So trying to combine the concepts of heat and energetics with and stoichiometry in a chemical reaction. So if you want the exact, it's going to be about 4 grams, but let's go ahead and do the exact answer. 4.13 grams CH4. So why don't you try it for 61 then? Just do grams, don't do kilograms. We're almost out of time. Oh, jeez. I'm off the way. So 15, 29, 61. All right, that's my shut up alarm. So I'll show you. I'll save you the surprise. It's this, whatever this is. Calculating it out. So 5.56. Convert that to moles. Multiply it by. Oh wait, it's 2 moles.
So then it's
For every 2 moles. Sorry, stoichiometry. Yeah. 2 moles there. So, yes, and thank you for the save. I realized it right when I walked up. Okay, so you're officially over class. So you're a minute over, so I need to stop the recording.